We're rolling. Okay, so this is our lesson for 6.2 today. And for 6.2, what I wanted to do is sum, difference, and double angle identities. And lucky for us, we get them all on our formula sheet. You don't have to memorize these. The honors version of the course that came before Pre-Calculus 40S, back when it was just called Grade 12 Math, actually it did have a code name. It was called Math 300. Not only did you have to memorize all these formulas, but you usually spent a couple classes deriving where they came from. And even though they threatened to, yeah, we might make you do one of those derivations on the test, we never had to do that. But I have a feeling in the honors version for sure they'd make you derive these formulas and prove that you understood where they come from. In this course, you don't have to prove where they come from. You don't have to memorize them. What you have to be able to do is recognize them. So these are the sum and difference identities. In other words, alpha and beta stand for angles. If I have the sine of an angle minus another angle, this formula will represent how much that value is. And that's true for these subtracted angles, and then these added angles. Meanwhile, when I say sine of 2 alpha, alpha being an angle, really that's like saying the sine of double an angle. Obviously, I'm not taking the sine of the number 2 and then timesing that by some angle. You kind of assume both of these things here are what you're taking the sine of. So if alpha was 30 degrees, then you're taking the sine of 60 degrees because you're doubling it. And there's your double angle identities. All right, let's just start getting into these. Example 1, simplify the following expression and give an exact value. So look at that rather bizarre looking statement. Does it remind you of anything? Look up and see what it looks like. Cos plus sine. Well, the only one up here that looks like cos plus sine is this guy. Cos plus sine. So I recognize that this thing looks like the cosine of alpha minus beta. And I'll just write it out. So it's the cosine of alpha times the cosine of beta minus the sine of alpha times the sine of beta. Because this looks like cos sine. So in other words, this is my alpha and this is my beta. Alpha, beta. And those are just Greek letters. You can say A and B if you like. So in other words, if alpha is pi by 3 and beta is pi by 12, then this is the cosine of pi by 3 minus pi by 12. And I can actually work with that. What is pi by 3 minus pi by 12? What's a third minus a 12th? Would it help if you changed it to a common denominator? 1/3 is 4/12 minus 1/12, which is 3/12. Are you okay with me shortcutting this? What's 3/12 simplified? A quarter? And hey, I know that. I had no idea what the cosine of pi by 12 was, right? It's not on my unit circle. It's not something I've memorized. It's not one of my special triangles that leads me to all those unit circle values. But I'm able to figure out this because of this lovely identity formula. And the cosine of pi by 4 is, of course, root 2 over 2. B is a throwback to one of the identities we did in the last lesson. What do you know? You know that sine squared theta plus cos squared theta equals 1. So it doesn't matter if theta is 47 degrees. It's like, oh no, that's not on my unit circle. Who cares? Cos squared plus sine squared of any angle is 1. So this thing is equal to 1. Over and done with. All right, C is kind of getting back to the stuff like A. I have to recognize that. So look up, where do you see 1 minus 2 sine squared something? Notice it's right here. You see that? 1 minus 2 sine squared alpha. So that's the formula I'm going to use. I recognize that this thing looks like this thing. So my formula is, I'll start out over here. They don't give me much room here, do they? The cosine of double some angle is equal to 1 minus 2 times the sine squared of just the single of the angle. So if I substitute in this 1 minus 2 sine squared pi by 8, then alpha is pi by 8. So that means that I can say that instead of cos 2 alpha, I know that this thing, so I can go 1 minus 2 sine squared pi by 8. I can say that that is the cosine of 2 times pi by 8. And again, that's one angle to me. What's 2 times pi divided by 8? It's once again pi divided by 4, which is the same answer I had in A. It's root 2 over 2. Okay, so that's how this stuff works. We look at the formulas and we recognize which formula we can replace our work with. The other thing we can do is we can start with an angle and then try to use the formulas. Check out example 2. We can use these formulas to determine the exact value of a trig ratio that's not on the unit circle. Like I said a minute ago, I don't know twelfths. My unit circle, I know thirds, I know quarters, I know sixths, I know halves. I don't know nothing about twelfths. But here's what I know about 7 pi by 12. 7 pi by 12 is 3 twelfths plus 4 twelfths. And I actually do know those two numbers. They're on my unit circle, right? Because this one is pi by 4 and this one is pi by 3. So I can rewrite the sine of 7 pi by 12 as the sine of pi by 4 plus pi by 3. And if I look at that formula sheet, the sine of alpha plus beta is, according to the formula sheet, sine of alpha times cos of beta no, is it a minus or a plus? No, it's a plus. Yeah, it's a plus. I don't have these memorized. Cosine of alpha times the sine of beta. So this is my alpha, this is my beta. Plug those things into that formula. So the sine of pi by 4 plus pi by 3 is, which is the same as the sine of 7 pi by 12, is sine of the first one, which is pi by 4, times the cosine of pi by 3, plus cosine of pi by 4 times the sine of pi by 3. And now I go to my unit circle knowledge. Sine of pi by 4 is root 2 over 2, correct? Cosine of pi by 3 is a half, right? Cosine of pi by 4 is also root 2 over 2. Sine of pi by 3 is root 3 over 2. And if you don't know those off the unit circle, you'd have to kind of work them out, right? You, just like the last couple units, you get a unit circle that's blank that you can figure things out with on your next test and guarantee you a question or two like this guy. So this is 2 times 1 over 2 times 2, root 2 times 1 over 2 times 2, so that's root 2 over 4. And root 2 times root 3 is root 6 over 4. And then I just have one last step. Do I want a decimal answer? No, not really. It does say it wants the exact value. As soon as you try punching the square root of 2 or the square root of 6 on a calculator, those are irrational numbers, right? So you don't get an exact answer, you get a decimal approximate. So my final answer, as weird as this looks, this is the simplest way to give this answer exactly in math. So that's it. That would be my answer for that. All right. If If anybody was sitting there wistfully going, oh, all these radians, I miss degrees. Okay, we'll make you happy. We'll go back to degrees for an example. Is 195 degrees on my unit circle? No. Notice that everything in the 30 degree and 60 degree families don't end in 5. So the fact that it ends in 5 tells me I must use the 45 degree family. So can you think of a combination of 45 degrees and something from the 30 or the 60 family that would add up to 195? What are you thinking? So say that again? So 345 degree angles, so 345, so that's 45, 90, so that's 135. That works. Is that the only one that works? Anybody have anything different? I was thinking this. That was you got? Okay, guess what? They should both work. Let's try them. Okay, so how about guys who got the same answer here? Try this one, and some of you can try that one. But of course, we're all using the same formula. The formula we're using is the cosine of alpha plus beta. And okay, you guys get to look it up, but I should know this. This is the one where it's plus in the left, but I think it's minus in the middle, isn't it? Am I right about that? I gotta check. Yay, it's minus in the middle. So it's cos alpha, cos beta, minus sine alpha, sine beta. So guys on the left side of the room, here we'll split this up into two solutions. Guys on the left side of the room, you're using this is your alpha, this is your beta. Guys on the right side, this is your alpha, this is your beta. And does it matter which one? Could I say 60 plus 135? Yeah, look at the formula. It actually wouldn't matter. So let's see. I'll do it twice. You guys try it on your own, and I'll see if I can work at your pace here. So the cosine of 135 plus 60 is cos 135 times the cos of 60 minus sine 135 times the sine of 60. Okay. Well, I know all of my 45 families are some sort of root 2 over 2. But is cos 135 positive or negative? X is negative over there. I think this is a negative. Cosine of 60 is, what is the cosine of 60? The sine of 30 is a half, so the sine of 60 is root 3 over 2. So the cosine of 60 is a half. Right? Minus sine of 135 is positive. And the sine of 60 is root 3 over 2. So I'm going to get negative root 2 over 4 minus root 6 over 4, which is negative root, which is negative root 2 minus root 6 over 4. Cool. Let's see if that's what I got using the other side. What if I used cos 45 plus 150? Then my alpha is 45, so cos 45 times cos 150 minus sine 45 times sine of 150. Okay, that's root 2 over 2. Cosine of 150 degrees is negative, wait a minute, cosine of 150. Oh, I'm having a hard time imagining that. So where's 150? Okay, I'll make a little sketch. 150 is over here. It's in the 30 degree family, so sine is 1/2, cosine's root 3 over 2. Right? Yep. But the cosine's negative. Minus root 2 over 2. Sine of 150 is positive, but at 1/2. Am I getting the same answer? Yes, I am. Negative root 6 over 4 minus root 2 over 4. And hopefully you realize that that's the same answer. Ta-da. So there we go. Doesn't matter, as long as you come up with something that's right, that works. Different people could come up with different values. So there we go. That was example 2. Now let's combine with what we learned in 6.1 and 6.2. In 6.1 we talked about non-permissible values. First of all, what are the non-permissible values now? Well, now I would say that the sine of 2 theta equals 0 is non-permissible, right? Because you can't divide by 0. And sine 2 theta, according to the formula list, is 2 times sine theta times cos theta. So if you have two things that multiply, 2 of course can only ever be a 2, but if you have something times something equals 0, you'd get a 0 if either of those things was a 0, right? So this would be non-permissible if sine was 0 or if cosine was 0. And that would mean that theta, your non-permissible values happen when theta is, okay, when is sine 0? At any multiple of pi, so 0, pi, 2 pi, so I'll say at pi times any multiple, where that multiple can be any integer. But when is cosine 0? Cosine 0 at any half pi, right? Pi by 2, 3 pi by 2. So theta is equal to any multiple of a half a pi. So that's actually the better answer, because it would include all the half pi's times any number would include the whole pi's. So there we go. So that would be my answer. Okay, so now it says simplify this expression to one of the 3 primary trigonometric functions. They mean make it just a sine, just a cos, or just a tan. All right, well, how am I going to simplify that? What do I know? I know that the denominator, sine 2 theta, if you go back to the formula sheet, and I don't feel like scrolling around, you go back to the formula sheet, you'll notice sine 2 theta only has one choice as to what it can be. So 1 minus cos 2 theta over sine 2 theta. I don't have any choice about this denominator. It is 2 times sine theta times cos theta. But notice cos 2 theta, I think they give me 3 different things on the formula sheet that cos 2 theta can be replaced by. Which one do I want? I don't know that it matters. I'll pick the one that says this. I'll replace cos 2 theta with 1 minus 2 sine squared theta. And let's see what happens. Well, if I have 1 minus 1, that constant's gone, right? 1 minus 1 is nothing. And if I take the minus of negative 2, I just get 2. And look at that. 2 divided by 2 is 1. And sine squared divided by sine leaves a sine on top. And hey, does that look familiar? What identity can I use now? Sine divided by cos is? I guess I don't have room to go to the right. I'll go down. Tangent. See how that works? So there we go. This whole big mush of an expression is just tan theta. All right. Oh, these are fun. I like these. If I tell you the cosine of an angle is negative 4/5, and I'm between pi and half a pi, and the cosine of an angle is negative 12/3 when you're between pi and 3 halves of pi, Find cos alpha minus beta. Okay, well, if I know the cosine of alpha is negative 4/5, I kind of, if I'm going to use this formula, what is this formula again? Well, let's write it down. Let's get the pen working. Come on, pen. Where are you? There we go. The cosine of alpha minus beta is cos plus sine. Right? That's my formula. So notice that I know cos of alpha, but I'm going to need to know cos of beta. And, oh, sorry, I know cos of beta. Sorry, let me say that again. I know cos of alpha, but later on I'm going to need to know sine of alpha. I know cos of beta, I'm also going to need to know sine of beta. So in other words, right now I could only find this part of the formula. I can't find this part until I know what these numbers are. And you've done stuff like this before. Even back in grade 11 you did questions like this. If you know that the cosine of alpha is negative 4/5, then think about what you know. Oh, and you also know that you're between pi and pi by 2. So that means you're in this quadrant here, right? C, A, S, T. You're in this quadrant where you're between pi and pi by 2. So if you're in this quadrant, you have a cosine of negative 4/5. That means that this line here, your x line, is negative 4, and your hypotenuse is 5, right? Because remember, cosine is adjacent over hypotenuse. So I can find my y using Pythagoras. So y squared plus negative 4 squared equals 5 squared. And y squared plus 16 is equal to 25. Y squared is equal to 25 minus 16, which is 9. There's probably people already kind of going, you know, I kind of could tell that was a 3, 4, 5 triangle, but they won't all be nice, easy numbers, so I'll show you the math. Square root both sides. Now remember that when you get to this point, y is equal to the plus or minus root 9, right? You have a choice here. Or maybe it's both. No, it isn't both. Which answer is it, the plus or the minus? What quadrant am I in? Oh yeah, isn't the y line here a positive line because I'm above 0? Yep. So ignore the negative, it's plus 3. And that means that my sine of alpha is opposite over hypotenuse 3/5. So there we go. Okay, your turn. What's the other thing they tell me? They tell me that the cosine of beta is equal to negative 12/13. Can you please figure out the same way I just figured out the sine of alpha, what the sine of beta should be? Little grade 11 review for you. Go. Okay, while you're doing that, I haven't done attendance yet. Here. All right, let's see if I can catch up to you now. Let me go back to my blog, to the meeting. There we go. And there. Okay, let me see if I can catch up to you. So, step 1, figure out where we are. We are in the quadrant where I'm between pi and 3 pi by 2. So I'm in this quadrant down here, or quadrant 1, 2, 3. I'm in quadrant 3. And in quadrant 3, tangent's the only thing positive, right? According to the cast rule. And so cosine is x, so x is negative 12. And the hypotenuse is 13. So I need to figure out what the y is. So y squared plus negative 12 all squared is equal to 13 squared. Y squared plus 144 is equal to 169. And again, some of you could probably knew when you saw the 12 and the 13 that it's a 5, 12, 13. But in case you didn't, or in case you see one later that's uglier numbers, you want this example to look back on, here's the math. And once again, plus or minus, but I know that y in this quadrant is negative. So my sine value here is negative 5 over 13. Any questions on how I got that far? Where did I lose you?
I got the right answer, but how did you get
Because it tells me right here that the beta angle is between pi and 3 pi by 2. So it has to be in this quadrant here. So this domain is what told me where to go. Does that work? Okay. Now that's not we're not done yet. This is just getting us ready to plug into this formula. So the cosine of alpha minus beta is cosine of alpha, which they gave us, right? Cosine of alpha was negative 4/5. I'll put it there for. And cosine of beta is the other number they gave us, negative 12/13, plus sine of alpha, which we just figured out is 3/5, times sine of beta, which we just figured out was negative 5/13. And now we do, and after all that work, if you goof up the arithmetic, it's going to make you feel very sad. But let's see, can I simplify this at all? Not really. I can do a simplification here, this 5 and this 5 cancel, but then I'd need a common denominator of 65 anyway, so I'm just going to leave it alone. So the common denominator here is 65. 5/13 is 65. Negative 4 times negative 12 is 48. And 5 times 13 over here is 65. But it is a positive times a negative, so I might as well make that minus. And 3 times 5 is 15. And so that's 48 65ths minus 15 65ths. And it's 33 65ths. No, you're not allowed a calculator. You should be able to handle that kind of arithmetic without it. And yes, we want fraction answers, not decimals. And that's it. That's how you do those kinds of examples. Okay, here's one more kind of like it. Check out the next one. So we're between 0 and pi by 2, and sine of theta is 3/5. Determine the exact value of sine of 2 pi. Okay, so the exact value of sine of 2 pi, there is only one formula they give me for sine of 2 theta, or sine, sorry, did I say pi? Sine of 2 theta. They only give me one formula for the sine of 2 theta. It's 2 times sine times cos. And I know sine, I got to find cos. So let's find cos together, shall we? We are between 0 and pi by 2, so we're in quadrant 1, right? 0, pi by 2. So we're in quadrant 1. And in quadrant 1, everybody's positive, so cosine will be no different. And sine is 3/5, so that means that I'm going up 3, and my hypotenuse is 5. So, you probably already know this. We won't bother. It's a 3, 4, 5 triangle. Okay, so x is 4, which means that the cosine of my angle is 4/5. So that's equal to 2 times the sine of theta, which they gave me, times the cosine of theta, which I just figured out. And 2 goes into 4 twice. I'm looking at 6/25. Did I not? Oh, wait a minute. Oh, hang on. That's not a denominator. Why did I do that? I don't know. Can I undo that? I'm going to undo that. Undo, 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 undo. Nope, the undos aren't working. Oh, now they're working. Sorry about that. That was terrible arithmetic. There. That's 2. Come back, pen. It's still not coming back. There we go. I don't know what I did, but the pen doesn't like me right now. I have no idea what's going on here. There we go. Pen kind of glitched on me for a sec. Hasn't happened in a while. It still put this back here, though, and this is interesting. 2 times that. There we go. Sorry, this is 2 over 1. It's not 1/2. I don't know why in my head suddenly that looked like a half. It's not a half. So that is 2 times 3 times 4, which is 24. 1 times 5 times 5. There we go. That's the right answer. Sorry about that. I need more caffeine. All right, cos 2 theta is, well, again, I have choices. You know what's nice about this one is, because I have choices, if I hadn't had to do A, where I had to figure out what the x value is so that I could get cosine, I could have done this question without doing any of that, because you can actually represent cos 2 theta using this formula. Oh, this hasn't happened to me in a while, but the pen is definitely glitching. Okay, hold on. There we go. 1 minus 2 sine squared theta. I can use that formula where I don't need any cosine. So it's just going to be 1 minus 2 times 3/5 squared, which is 1 minus 2 times 9/25, which is 1 minus 18/25. And of course, 1 is 25/25, right? So my final answer is 7/25. No, you can't use a calculator, and no, you can't switch to decimals. Okay, so there we go. There's the calculation type questions. So that's kind of combining our new formulas in 6.2 with the stuff we did in chapter 4 and in 6.1. Now let's combine our new formulas with what we did in chapter 2. Let's use them to prove identities. Okay, now, which side to you looks the most complicated? That's kind of a tough question right now. Like, I don't know, they both look kind of complicated right now. I don't really know which one I'd say is more complicated looking at that. Well, I think the right-hand side is definitely more complicated because it's got double angles in it. So I'm going to leave this one the way it is. And this side here I'm going to start kind of attacking. So once again, sine 2 theta, I have no choice. I have to just change that to 2 sine theta cos theta plus sine theta. And of course, there's nothing I can do with minus cosine right now. But I'm looking at this, and I'm thinking to myself, look at my formula sheet. I've got 3 choices. Which of those 3 choices is the one I want? Well, my goal is to not have this fraction thing anymore. And I actually kind of noticed something. Ooh, here's what I noticed. Look what I noticed about this denominator. I notice I can factor the denominator. I'm going to go down here and factor sine theta out of the bottom. And I got 2 cos theta plus 1. So I'm thinking if I had, or if I used something where I could find this, it would work really well. So I'm actually going to use, for the cos 2 theta, I'm going to replace cos 2 theta with 2 cos theta minus 1. So I'm replacing this with that from my formula sheet. And again, go back to the formula sheet. You had 3 different things you could have used. Why did I use that one? Well, because I notice that if I now rearrange that, this thing has that as a factor in it. Think of this thing here, if you like. Think that this is like 2x squared minus x minus 1. That factors into 2x plus 1 and x minus 1. So I can factor this numerator into 2, oh, there we go again, into 2 cos theta plus 1 times cos theta minus 1 all over sine theta times 2 cos theta plus 1. And now that everything's in factor form, you can't cancel terms, but you can cancel factors. Anything divided by itself is 1. So I now have cos theta minus 1 over sine theta. And there might be people looking at that going, hey, that still doesn't look like the other side. Oh, use your imagination. It's exactly the other side. Because if you're over a common denominator, you can actually split it apart. Have you ever undone a common denominator before? Like all operations in math, you can undo them if you can do them. Does everybody get how this line is equal to that line? And do you see where that's going now? Isn't cosine over sine cotangents? And isn't 1 over sine cosecants? And again, sometimes, I think I told you this earlier this class, right? Sometimes people who teach this course like you to end a proof with PAR. You don't have to if you don't want. Proven as required. And that was a really hard one, so you can show off a little. Proven as required, so there. No, don't do that. I'm just kidding. Don't do that. It's PR. Okay, so that is about as tough as proofs get. I had to deal with factoring. I had to think of undoing a common denominator. That one took some imagination. That one was fun. Let's do one more tough, ugly one using our new formulas. Once again, you're probably looking at that going, oh, I'm going to work with the left side because it's way more difficult looking. Okay, you could. Or you could start on the right side because you have a double angle. Tell you what, I'll work the left side. Let's go to here. We'll leave the right side alone and we'll see what we can do with the left side. 1 minus tan squared theta over 1 plus tan squared theta. Okay, what can I do with this mess? Well, the first hint, I believe, on my list of hints in the last notes was, when you can, change everything into sines and cosines. So what is tangent again? Tangent is sine over cos. Right? Now, I have to somehow make this thing way simpler. I have to combine it into a single thing because at the end of the day, this is a single thing. So I think what I'm going to do is I'm going to use common denominators. Right? I'm going to times this 1 by 1. It's just that my 1 is going to be this. And I'm going to times this 1 by 1, which is going to be the same thing. And now I'm going to have cos squared theta minus sine squared theta, right? Because when you times this by 1, you get that. All over cos squared theta, because it's a common denominator now. So that took care of this part. This part here just became that. Divided by, and let's see, so the denominator will be cos squared times 1, which is cos squared, plus sine squared, all over cos squared. And at this point, some people sometimes will just do a shortcut. They'll say, oh, I know what's going to happen when I times by the reciprocal. Those two denominators will cancel. If you want to just cancel there, you can. But I'll take the time to actually write this out. Right? Dividing by a fraction is timesing by its reciprocal. And cos squared divided by cos squared is 1. And then if you're crazy and you go, oh, and then I can cancel that cos squared with that cos squared. No, you can't. And remember, when you miscancel, God gets angry and kills like a small kitten. So, no, you can't cancel terms. You can only cancel factors. So I'm kind of stuck with my numerator being cos squared theta minus sine squared theta, and my denominator being cos squared theta plus sine squared theta. Right? I can't cancel any of those guys. They're not factors, they're terms. But I actually have my answer staring me in the face. Can you see it? There are 2 steps here to getting to my answer, my right-hand side. What do you know about that denominator? What's sine squared plus cos squared? Our most important trig identity. It's 1. This whole denominator is 1. So I can just ignore it. Dividing something by 1 is nothing. And what can I do with this? Look at my formula sheet. Isn't that one of my choices for cos 2 theta? So there it is. There we go. That's how tough these proofs can get. They're fun. They take work. They take logic, reasoning, and good algebra skills. But I don't know. Some of us think this is one of the more fun parts of the course. Okay, I'm going to actually, I'm not going to even stop my video. This is the bonus part of the video. Lesson 6.2 is over. Notice you've hit some textbook questions, but of course you have the worksheets in your booklet to do. Think of these as extra practice if you want. I did want to go back. Somebody, I think there was only a couple people left in the meeting yesterday when it was pointed out to me that there's a mistake on the 6.1 answer key, and I actually did want to talk about it for a sec, because it's kind of an important kind of idea for 6.1. Let me just go back to it. In 6.1, so guys, if you're watching the video and you're just here for the 6.2 video, you can just turn it off, but here's some bonus stuff about 6.1. They have the wrong answer for D. If I'm doing D and I'm trying to find the non-permissible values, I know what they're thinking. They're thinking, oh, cotangent is 1 over tangent. And 1 over tangent, well, tangent would be 0 at pi by 2. And you can't divide by 0. So they actually say in the answer key that pi by 2 is in fact a non-permissible value. And that's actually wrong. And I'll show you why that's wrong. Here's my proof here for you. I'm going to go to Desmos. If I can make Desmos come back up. I know Desmos. Okay, so first of all, think about what y equals x looks like. Y equals x is a straight line, right? And because you can't divide by 0, what happens when you take a reciprocal of it? Well, this point here that's a 0 becomes an asymptote, right? Remember that? You've seen those graphs before. Okay, well, I'm going to do the same thing with tan. Tangent's this funky looking guy. And yeah, tangent doesn't exist at pi by 2. But that doesn't mean that it doesn't exist when you take cotangent, because the reciprocal of an undefined, if my undefined is 1 divided by 0, the reciprocal of that is 0. Cotangent does very much exist at pi by 2. In fact, it's an x-intercept. So the right way to do that question, I maintain, is to do what it said back in hint number 1 in the 6.3 lesson. Switch this to cos over sine. That's what cotangent actually is. And then say, okay, sine of x can't be 0, because then you'd be dividing by 0. And sine x plus 1 can't be 0. So my non-permissible values happen at 0, pi, 2 pi. Of course, it's saying, it says this is for over the real, so I'll just say that my non-permissible values are any pi times k. And my non-permissible values for this happen when sine of x is equal to -1. When is sine of x equal to -1? That's at 3 pi by 2, right? But times k, where k is an element of integers. So it's any integer multiple of 3 pi by 2. Pi by 2 does exist, and again, I can prove it. I think this is the right answer, not what they have, and I can prove it. They include pi by 2 as part of the answer that doesn't exist, but they're wrong, because, look at this. I actually did graph this thing, and it exists just fine at pi by 2. In fact, again, it happens to be x-intercepts, but it doesn't exist at 3 pi by 2, or any integer. Actually, I just realized I wrote that down wrong. Let me fix that. It's not times k, it's plus 2 pi k, where k is an integer. Because you can exist at pi by 2, but not at 3 pi by 2. You can exist at 5 pi by 2, but not 7 pi by 2. So the right way to do all of these questions is to not think in terms of tangent and cotangent, because they're weird. Think in terms of sine and cos, and always go back to, hey, it's only a non-permissible value if I'm stuck dividing by 0. So I only have to worry about that and that. So that's kind of a good rule of thumb for this. All right, now I'll stop my video. Bonus content over.